We can do this by modeling this as a chemical reaction. So we're going to label our adsorbate molecule as A and our solid as S. So in any chemical reaction, we've got two reactants, our adsorbate and our surface. And in this model, we're going to say that this happens as one step. It's a one-step process, and we have an elementary step forming an adsorbed molecule on the surface. So we're imagining that the product of this reaction is a molecule sitting on the surface. And for our purposes, we can apply this to physisorption or chemosorption as long as it's a single step. So we have, for the forward process, a rate constant K1 and a backward rate constant K2. And so we can say the forward rate, or adsorption rate, is equal to, since these are single elementary steps, we can get the molecularity by looking at the mechanism, and then we can turn that into the order of the reaction. So we can see it's going to be K1 times the concentration of A times the concentration of surface. Okay, that sounds crazy, but we'll come up with a fix for it in a minute. So we'll just leave that for now. The desorption rate is going to be K1 prime times the concentration of adsorbate on the surface. Okay, great. So it all looks great except for how do we quantify the concentration of surface? Or the concentration of stuff on the surface? That just seems a little strange. So what we're going to do is imagine a surface as like a checkerboard with a certain number of sites on it. The squares represent sites. And when we put adsorbate molecules on there, it's going to occupy a site. Once we have this notion of vacant sites and filled sites, we can define something called the surface coverage theta. And theta, we're going to define this as the fraction of sites that are filled. So if we put checkers on all these squares, theta would be equal to 1. If we didn't have anything, it was just a blank board, theta would be equal to 0. So theta is always going to be, when we're restricted to monolayer coverage, theta is always going to go between 0 and 1. Great. We're going to use that as a way to define concentration of the surface. So we can use theta as a measure of how much stuff we have on the surface. The higher the value of theta, the higher the value of adsorbate stuck to the surface. On the other hand, the lower value of theta, the less stuff we have on the surface and the more free surface we have. So we're going to be substituting expressions for theta for surface covered and free. So the adsorption rate is going to be K1, concentration of adsorbate, and then we're going to replace concentration of free surface with 1 minus theta, the fraction of the surface that is free. So if theta is equal to 0, there's nothing on the surface, and so the entire surface is free. The desorption rate I'm going to rewrite this equation, except for we're going to replace this concentration of covered surface with just theta. Because if the concentration of covered surface is higher, the fractional coverage is higher. All right, now we have to remember that at equilibrium, what's going to be the relationship between those two rates? Well, at equilibrium, the off rate and the on rate have to be the same because there's no net change. So at equilibrium, we can write K1 concentration of A times 1 minus theta is equal to K1 prime times theta. Let's gather the constants on one side. So we'll divide both sides by K1 prime. So we have K1 over K1 prime is equal to theta over 1 minus theta. And we have to divide both sides by the concentration of adsorbate. We can recognize this is just the equilibrium constant, the forward rate over the back rate. So we'll call this K for adsorption. Notice we're writing it as a large K now. It's no longer a rate constant, it's an equilibrium constant. So KAD is equal to theta over 1 minus theta, the concentration of adsorbate. And we should be a little bit careful here. These are equilibrium values, right? We're no longer doing it as a, these are equilibrium values. Okay. At this point, we can solve the equation for theta. This is the form of the Gibbs adsorption isotherm you usually see, solved for theta. So it shows us how the surface fills up, how the surface coverage varies as we increase the concentration of adsorbate. Let's look at the properties of that. So theta is equal to K adsorbed concentration of A over 1 plus K adsorbed concentration of A. So how does that play out in terms of, if we look at theta at concentration of adsorbate, we can see that at low concentrations, this term is going to be small compared to 1, which means that this isn't going to matter. This is all going to be roughly equal to 1, which means that there should be a linear relationship between theta and the concentration of adsorbate. So we get something that looks like this, a straight line. However, as this gets bigger and bigger, eventually 1 becomes negligible, and then the bottom is approximately just Ka, and the top we have Ka, which means, of course, theta is going to asymptote out at a value of 1. So we get a curve that looks something like this. If we want to make a linear graph, we can just take the reciprocal of both sides. So we get the reciprocal of the surface coverage. If we take the reciprocal, we can see you have 1 over Ka, and we have Ka over Ka. So we have 1 over Ka plus 1. So this should give us a linear graph, and if we graph this, we've got a reciprocal coverage on the y-axis and reciprocal concentration of adsorbate on the x-axis. You get some sort of curve like this. We can see the y-intercept is going to equal to 1, and we can see the slope of our graph is just going to be the reciprocal of K adsorption. On the next screencast, we'll do an example.